to talk about electrophilic addition to conjugated systems. We're going to talk a little bit about kinetic versus thermodynamic control, and we're going to talk about the Diels-Alder reaction. I'm going to go through these fairly quick because this is part of our inverted lecture, so you need to view this prior to coming to class on Monday. So if we think about electrophilic addition, when we've discussed it in the past where we just had a single carbon-carbon double bond, all we had to worry about was how the two pieces added across the carbon-carbon double bond. Did one piece add to carbon 1 or did the other piece add to carbon 1 or 2? And so everything was pretty simple. We just had to follow Markovnikov's rule. When we have conjugated systems, however, addition chemistry can actually get more complicated because you can actually add reagents across multiple atoms of the conjugated system. So if we think about this isolated diene that we have here, so we have, if we count it, 1, 2, 3, 4, 5 carbons. So this is 1, 4 pentadiene. And if we were able to be very, very careful and add just one equivalent of hydrogen bromide to the reaction mixture, we would simply add HBr across one of the double bonds. It doesn't matter because it's symmetrical, so it's just showing that it's adding to this one. And we know from Markovnikov's rule that the hydrogen will go to the least substituted carbon and the bromine will go to the more substituted carbon, to a carbocation intermediate. And so you would end up with the product that you see here. Pretty simple and straightforward. Since the double bonds are not in conjugation, it just behaves as an isolated diene. So we end up with an alkyl bromide and an alkyne. However, when we go to a system like this, where we have 1, 2, 3, 4 carbons, so this is 1,3-butadiene, if we were to add HBr across it, what we would actually find are two different products. We would end up with a product where we simply add the hydrogen to carbon number 1 and the bromine to carbon number 2, which is what we call a 1,2 addition product. Very similar to what we saw before, but we'd also get a product where we would add the hydrogen to carbon number 1 and the bromine to carbon number 4, what's known as the 1,4 addition product. And the reason that this happens is because these two pi bonds are actually in conjugation with one another, and it's really one pi system. And so you can imagine getting two products. The 1,4 addition is also known as conjugate addition because it's adding across a conjugated system, whereas 1,2 is also known as simple addition. Now, it turns out that reaction conditions make all the difference here. So for example, if we take our 1,3-butadiene and HBr, and we take this down to really cold temperatures, like -80, okay, so putting it in a bath of dry ice and acetone will get us to -78, so something kind of like that. And we add that one equivalent of HBr, what we'll find is that we get 80% of our product is going to be the 1,2 addition product, and only 20% is going to be the 1,4 or the conjugate addition product. However, at high temperature, we see exactly the opposite. At high temperature, we see 20% of the 1,2 product and 80% of the 1,4 product. And it also turns out to be very interesting that if we take this 1,2 addition product that we isolated at low temperature, and we heat it up to 40 degrees, eventually it will equilibrate to the 1,4 addition product as well. Okay, as you can see here. And so what this means is that this 1,2 addition product is also known as the kinetic product, meaning that it forms the fastest. And since it forms the fastest, it always forms first. Whereas the major product that we would get upon heating it would be the thermodynamic product, the 1,4, meaning that this is more stable. Now, I'm not going to tell you exactly why this is more stable right now, but I want you to think about it before you come to class on Monday. Why would the 1,4 addition product here be more stable than the 1,2 addition product? So give that a lot of thought. I'm going to start Monday with that question. Okay? And we'll talk about that a little bit. So I'm not going to go through the problems. I also want to talk about the Diels-Alder reaction. The Diels-Alder reaction is also known as a cycloaddition reaction. It is a very, very useful reaction. It was actually discovered in the early 1900s. And the two chemists that were responsible for this did win a Nobel Prize. If you think about it, it's taking a diene, a conjugated diene, so in this case 1,3-butadiene, reacting it with an alkene, if you will, and clicking the two together such that you get a six-membered ring. They quite commonly refer to these as adducts. But what you'll know is that this is also called a 4+2 pi electron cycloaddition reaction, or a 4+2 cycloaddition. The reason is that you've got 4 pi electrons in one piece, you've got 2 pi electrons in the other piece, and these are coming together to form the six-membered ring. Now the easy way to think about this is by pushing these three arrows that you see here. The alkene reacts to form a carbon-carbon bond here. This bond moves to form the new pi bond here, and then this pi bond reacts to form a new carbon-carbon bond. This reaction actually lies to the right, although sometimes you have to beat on these to actually get them to go very well. And the reason is that we've got 3 pi bonds, right? And we're gaining 2 strong sigma bonds at the expense of 2 pi bonds. So we end up with a new pi bond in the product, but nonetheless, we end up with stronger sigma bonds, and this reaction lies to the right. Okay, and so we have what's known as a diene. Notice it has to be in the S-cis conformation. We talked about that the other day. And this is the dienophile. The cool thing about this reaction, if you really think about it, if you look at all the atoms in the starting material, all the atoms are in the product. This is a perfect example of a atom economical reaction. There's no waste in doing this, at least from the reagent's point of view. Everything that we toss into the reaction mixture ends up in the product. Also notice what we're making. We're making carbon-carbon bonds. And I've told you there's only a handful of ways to make carbon-carbon bonds, and this is one of them. And we're forming six-membered rings, which are very, very important in biological systems. Also interesting to note, this is as far as we know, this is a purely man-made reaction, because we have yet to find an enzyme that can actually catalyze the cycloaddition reaction, or the Diels-Alder cycloaddition reaction, which is kind of cool. People are still looking for enzymes that do this, because you might think, given the number of six-membered rings that are in biological systems, that Mother Nature would choose to do something that is so atom economical. The problem is Mother Nature actually goes through other routes to make six-membered rings that are just a lot easier. To do this particular reaction, you would have to take these two reacting partners and actually heat them up to about 150 degrees. That's why we probably can't find an enzyme that does this. There's just not the energy in a biological system to do it this way. So, for example, dienes that really work really well are things like 1,3-butadiene. You can have some substituents on it without any problem. Notice that in the dienophile, we typically have things like carbonyls, like aldehydes, esters, or these anhydrides, which are really kind of just a shared ester, if you will. And these are known as electron-withdrawing groups because of the carbonyl. Of course, the carbon has a partial positive charge on it. And it turns out that that helps facilitate the reaction. And so what you can see is we are forming these nice six-membered rings very, very easily. So go over this on your own. Basically, anytime you have a 1,3-diene, if it's in the S-trans configuration, you need to rotate it to where it can be in the S-cis so that it will react with the dienophile. This does not react with the dienophile. It has to be in the S-cis conformation. Think about it by building a model, and you'll see why that has to be the case. Excuse me. So, for example, cyclopentadiene is a very reactive diene in the Diels-Alder reaction because 100% of the diene is in the S-cis conformation. If you look at this diene, this is a conjugated diene, but because this is a fused ring system, I can never rotate around this bond to get these two carbon-carbon double bonds in the S-cis conformation. This would be unreactive in the Diels-Alder reaction. Okay. Also of importance in the Diels-Alder reaction is that the stereochemistry of the alkene is preserved in the product. So for example, if you see here, we have maleic acid, where the two carboxylic acids are actually on the same side of the alkene. When the Diels-Alder reaction occurs, the two carboxylic acids will again be on the same face of the system. So here they've drawn them going back and out towards you, but it's a cis product. We have them cis in the starting material. We have them cis in the product. This is a stereo-specific reaction. Okay, you need to look that definition up. Also, if you take fumaric acid, which is nothing more than maleic acid, but in the trans configuration, or conformation, excuse me, you can see now that the carboxylic acids are trans to one another. 100%. Okay. We'll talk about this in class. Go through and look at how you can form these bridge systems, so these bicyclic compounds through a Diels-Alder reaction. Review these facts. And again, steroids can be synthesized using the Diels-Alder reaction. If you look, we've got a bunch of six-membered rings in these systems, and that's where the Diels-Alder reaction has actually turned out to be quite useful. And so, for example, you can imagine making estrone and cortisone by this method fairly easily. So you have a diene, you have a dienephile. This reaction occurs, you form the new six-membered ring, and then through several steps that we won't talk about, you can actually take this to estrone. Same kind of thing here. You can take this dienephile pair, make the six-membered ring that you want, and then do a variety of chemistries to actually get to cortisone. So we're going to go through these as well on Monday. Have a good weekend, and I will see you in class.